Newton was a little picky about how he named things and called things. He invented the word linearization because he didn't like the word tangent line. Because to him, like, tangent line was confusing. Are you talking about trigonometry? Are you talking about that tangent? Or geometry? Like, he didn't like the connection to trig and geometry that a tangent line normally had, so he decided to give it a new name. Linearization, it's the same thing as a tangent line. Okay? So you've done tangent lines before, it's just his name of what he called it. All right? Okay. So he used the notation L of x. It really just was his tangent line. He called it a linearization. Every tangent line that you create needs what two things? We've done this before. Okay. Every tangent line needs, all right, what two things? A point and a slope. Okay. If you've got those two things, you're good to go. Now, let me talk you through a little bit of a visualization of what Newton used linearization or tangent lines for. Okay, go ahead and create a curve. We're going to call it f of x. And we're going to pick the spot A. And that's where we're going to create our tangent line. So this linearization process is creating something that has a parallel slope at that point A. And so this is what we call L of x. So we have L of x and f of x. And this is where the beauty of that I can zoom way in into mine, but you guys can't really. Okay, if I zoom pretty far into this, is there any negligible difference between L of x and f of x? As far if I zoom in, where are they exactly the same? At A. They're exactly the same at A. Okay? All right. How long do they say reasonably close? Right? Is this reasonably close? How about that? Can you start to see a gap? Okay, and if it, now you're seeing the gap, right? Okay, so visually, you know, we're saying, oh, it's reasonably close if I can maybe, oh, I don't know, maybe I can go a little farther, like from there, maybe to there. Maybe I can get that a little farther. Can I get it maybe, maybe here before I start to see the separation? But for sure I see the separation here. Okay. Okay, now I'm going to have to draw those a little darker. All right, so Newton's idea was close enough. As long as you're close to A, use a tangent line to find the answer instead of using the function. It'll be easier. The math will be easier if you're using a tangent line instead of, as long as you're close enough. But you have to stay close enough until the gap becomes significant, because the function has concavity, but the linearization doesn't. Right? And the concavity of the function is pulling the function away from the linearization so that the function is below. So if you stayed on the linearization, you would be too high. You'd miss your mark. Okay? You would overestimate because the concavity of the function is pulling you in that particular direction. Okay, suppose you placed your linearization elsewhere. Suppose you decide, okay, let's make a linearization right here. Okay, I'm going to create my linearization. I'm going to try and match my slope as best as I can. And again, if I zoom way in on that point of intersection, okay, color that in a little bit better. Okay, zoom way in on that. They are reasonably close to each other for a little while, but the gap is pretty evident right away. What kind of concavity does the white function have at that point? Positive concavity. And so the positive concavity is pulling the separation, it's making that separation between the two grow, and so the tangent line will always underestimate it. It's always going to shoot underneath where your function is because the concavity is pulling the other graph away at a faster rate. It's curving away. The idea of underestimating and overestimating is huge in the idea of Newton's linearization. You will always be asked two questions. Find the linearization and then predict if it's an overestimate or an underestimate. Those two questions always go hand in hand. All right, so let's talk about that a little bit. If point A is on a section with negative concavity, on a section of f of x, all right, as it is in our picture, point A is on a section with negative concavity, then L of x will always exceed or overestimate f of x. And so you're going to answer those questions always based on what kind of concavity that particular section of the function has. So the converse is true about point B. So if point B is on a section of f of x that has positive concavity, then that L of x right there will always underestimate or underapproximate f of x. So a lot of times, sometimes you'll just like quick sketch a little picture. I'm concave down, and a line is going to always, the linearization will always be outside of that concavity or above or exceed the concavity. Okay, so what we're going to do right now is we're going to practice creating a couple, comparing the actual values, and seeing that we overshoot or we undershoot the actual value. All right, here we go. Let's work on a square root. Okay, given f of x equals the square root of 1 plus x, use L of x to estimate f of 3. Okay, use L of x to estimate f of 3. Now we know what f of 3 is, right? If we plug 3 into this, we can see that 1 plus 3 is 4, square root of 4 is 2. But I'm picking a problem that has an easy result just to illustrate how the Newton's calculus would work out. All right? Clearly, Newton would not have used his linearization method if he could just figure out the square root of 4. But we'll also use it to figure out a different square root that's not quite so easy. Okay, so to create our tangent line, we need a point and we need the slope. All right, our point clearly is 3, comma, 2. Our slope, using the derivative, will be 1/2 1 plus x to the negative 1/2 times the chain rule of 1. If I plug 3 into that, I will get 1/2 times 4 to the negative 1/2. That's the negative the reciprocal of the square root of 4, so that's 1/2 times 1/2, or 1/4. All right, so we have our point, we have our slope. Let's create our tangent line. So y minus the y value of the slope is 2. Excuse me, the y value of the point is 2. 1/4 times x minus 3. Okay, now I want to kick the 2 to the other side. I don't have to distribute, just kick the 2 over, so you have plus 2 like this. In this form, this is called a linearization. Okay. So, this linearization should estimate, or should give me the same answer for f of 3. What if I plug 3 into this? Okay, well, if I plug 3 into this, clearly 3 minus 3 is 0, times half is 0, add 2, I still get 2. It perfectly estimates the value of f of 3. But now let's use it f of 3.05. Okay? So tell me the square root of that. Okay? So if I try to plug 3.05 in directly, I'm going to get 1 plus 3.05, which is going to be the square root of 4.05, which I can tell you it's close to 2, and it's more than 2, but I have no idea exactly what that is. I could guess. But the linearization is going to get you very, very close to that. Okay, so this is boo. Don't like to do that without a calculator. All right, so let's try L of 3.05. All right, well, if I try L of 3.05 instead, that's 1/2 times 3 minus, 3.05 minus 3 plus 2, which is, oh, did I just copy the slope wrong? Oh, I did. You're right. I had it right when I wrote it, and then I somehow dropped it. Okay. 1/4, 1/4. Okay. All right. 1/4 of 0.05 plus 2. All right, well, I'm going to switch to fractions because 0.05 is 1/20th plus 2, so 1/80th plus 2, so 2 and 1/80th. All right, that's my bet. I'm betting that the square root of 4.05, which is the actual function, is going to be pretty darn close to 2 and 1/80th. All right, now, how sure am I? Well, now I want to think about the concavity. This little square root graph that I'm working on, can you picture a square root in your head? What kind of concavity does the square root have? Okay, what kind of concavity is that? Negative concavity, right? Okay, if this is negative concavity, then my estimate from my linearization should be an under approximation or an over approximation. It should be an over approximation, not by much, but it should be an over approximation. Okay, so since f of x is concave down, my L of 3.05 will overestimate, will be greater than my actual f of 3.05. In other words, 2 and 1/80th is going to be greater than the square root of 4.05, but not by much. So I'm going to overestimate it. Now, we have a calculator at our disposal, so let's actually check what the values of these are. Okay, so let's check what 2 and 1/80th is. All right, 2 and 1/80th is 2.0125. The actual square root of 4.05 is 2.01246. Look at how close that sneaky little Newton was. Okay, he was accurate to the tens, hundreds, thousands, 10,000 decimal place. Okay, and he was only over by 4/100,000ths of a decimal place was all he was off by. Okay, and we did all that without our calculator. Okay, so he was super accurate with this without having the luxury of having a calculator. He knew he was over, but not by much. Now, this only works because how close are 3 and 3.05? They're very close to each other. Would this work for the number 3 and the number 4? No, the gap in that is too big. Okay, you have to be near an integer in order, or near a whole number for, near an integer value for this to work. Okay, but as long as you're close, as long as you're within what we would consider to be a reasonable distance away from that target point, then Newton's linearization will always work to approximate values for you. Okay, let's try another one. Okay, all right, let's consider not a square root, but let's consider a quartic function. All right, so let's be given the g of x function to be 2x to the 4th plus 4x minus 3. Use an L of x to approximate f of negative 0.9. Okay, so again, the argument is here. Would you like to plug negative 0.9 into g of x directly without having access to a calculator? Okay, like, ew. I mean, that's negative 0.9 to the 4th, and then, okay, don't want to do that. So let's try creating a linearization at a nearby integer and know that we will be pretty darn close. Yeah. Oh, yes, thank you. All right, what integer would you like to pick? Sure. Okay, let's create a linearization, L of x, at x equals negative 1. So I just need a point, and I need a slope at negative 1. All right, well, I don't mind plugging negative 1 into that function. That's no problem. Okay, so my point will be, okay, if I plug negative 1 in, and then I plug negative 1 into the function, that's going to be 2 times negative 1 to the 4th, plus 4 times negative 1 minus 3. What do we get? A little quick mental math. Two times negative 1 to the 4th, plus 4 times negative 1 minus 3. 2 minus 4 minus 3. Negative 5. All right, thank you. Okay, so our point is negative 5. Now we want to find our slope. And I don't mind finding my slope here either. My slope will be 8x to the 3rd plus 4. I'll plug negative 1 into that. So 8 times negative 1 cubed plus 4. That's negative 8 plus 4. So the slope is what, ladies and gentlemen? Negative 4. And so my y will be plus 5, slope of negative 4 times x plus 1. And then to put it in linearization form, you don't have to distribute, you just have to move the minus 5 to the other side. So it would be y equals negative 4 times x plus 1 minus 5. So this is called the linearization in that form. It's a lot easier if you don't distribute, because if you don't distribute, and you plug your negative 0.9 into this, having that parentheses there is going to make the math a lot easier for you. All right, so let's plug, since I don't want to plug negative 0.9 into the g function, because that would be really hard math, I will plug it into the L of x function instead, and I'd rather do the math there. So negative 0.9. So this would be negative 4 times negative 0.9 plus 1 minus 5. Okay, I don't mind that math, because negative 0.9 plus 1 is very easy for me to do. So that just gives me 0.1. So I get negative 4 times 0.1. I can do that math too. That's negative 0.4 minus 5, which is negative 5.4. All right, so I am saying that the L of negative 0.9 is going to approximate the g of negative 0.9. But I also want to know which one is going to be bigger. So thinking about this particular function, it's a quartic function, which behaves like a parabola. What kind of concavity will I have of this particular function? Okay, and if you're not sure, you can always do the math on it. Okay, just move over to the side and say, okay, I'm going to find g. I've already found g prime, right? G prime was 8x cubed plus 4. And so then g double prime on that would be 24x squared. So if that's the second derivative, then no matter what number I plug into that, what kind of concavity value will I get? I'll always have positive concavity. All right, so since g has positive concavity, that positive concavity will be pulling the g function away from the linearization. The positive concavity will sort of suck it, all right, and suck it in an upward direction. So L of x, our L, will always underestimate the g. So we're saying we think it's negative 5.4, but we're willing to concede that that will be a slight underestimation. Okay, we're willing to concede that. All right, now can you use your calculators for me and go ahead, now that you have the luxury, check what negative 0.9 is actually in the g function and tell me how close we were. So negative 5.4 is what we got, and our question is, since we have a calculator, check it. How close were we? So you're just plugging negative 0.9 into the original function. Did anybody figure that out yet? Okay, negative 5.28, say it again? 78. All right, so negative 5.288, can we say? Okay, and so yeah, negative 5.4 is lower than that. Now, this wasn't quite as spectacularly close as last time. Why not? Okay, and how far away are negative 0.9 and negative 1? A tenth, right? Last time, we only used something that was 500ths away, okay? So it was closer. So the closer you are, the more accurate you will be. Now, sometimes you don't have the luxury of picking something as close, but so we're getting into that danger zone. Yeah, this is reasonably close. It's a good enough estimate. Okay, it would not be good enough, like your boss would probably, if you were off by this much, okay, and my design's got to be perfect, so you might want to be a little bit more accurate than that, so be closer. But in Newton's day, when they didn't have calculators or computers to do it, for sure, this was a great estimate of the value. Okay, so Newton, pretty smart guy, knowing how to cheat the system, basically. Okay, little kind of fun story. They'd have like these little math competitions. They'd like say, find the square root of 17, right? And everybody'd be real busy and all trying to compute the square root of 17. He had come up with calculus. And so he just made a little linearization. Oh, square root of 17, that's pretty close to the square root of 16. I'm going to make a little linearization. Boom, he'd come up. And he could beat all these people in these competitions. They could not figure out what the heck he was doing. He was doing it so quickly with such great accuracy. All right, so, and then he published, and then he finally told people what he was doing. All right, so he figured out how to put calculus to his advantage. Okay, that's no problem. Let me show you how Leibniz did it, because he came up with his own way. He just used dy instead of f prime. Yeah, no problem. All right, you'll find it pretty simple. Okay, here's how Leibniz would do it. X squared plus 4x minus 7. We know that Leibniz's way was not to use primes, but he wrote dy dx, right? All right, and so dy dx would be 2x plus 4. He decided, oh, I'm going to cross multiply that. I'm going to put 1 under here, and I'm going to cross multiply, and I'm going to get dy and parentheses 2x plus 4, and then I'll put my dx over here. So I'll use it like a cross multiplication. dy is what he called a differential on y. It was an estimate, just like Newton came up with, but he called it differential. So this is called differential of y. And then the other one he called the differential on x. Differential means how much is it different? And so Leibniz would say, well, if I'm going to slide across the graph different by a 1/10 or different by 5/100, then how much would my y be different? If that's how if the difference in my x is this, then what will the difference in my y's be? That's basically how he treated it. Okay, so let's say that we're focusing on x being 1, but we want to slide with a differential of x, and we want to go 0.05 away. How will that affect your y value? You just drop those numbers in. 2 times 1 plus 4 with a differential of 0.5. I prefer fractions, so I'm going to say that's 7, and this is 1/20th, so 7/20ths. So if you move 5/100ths away from your present y value, present x value, your y value will correspondingly change by 7/20ths. You do have to know what the y value was, but that's easy. You can plug 1 into the original equation. The original y value is 1 squared plus 4 times 1 minus 7. So that's 1 plus 4 is 5, minus 2 is negative 2, minus 7 is negative 2. So your original y value is negative 2, so you will now change that by 7/20ths. So that was how he would use his predictions. Does that make sense to you? Okay, so the old point is 1, negative 2. The new point would change the 1 by 0.05, and it would change the y to negative 2 plus 7/20ths, and that will be the new y. He focused on how much it changed. The underestimate and the overestimate is still the same. It's still based on concavity. Okay, it doesn't. So he would, this is a parabola. Parabolas are concave up, so my estimate will be under what it should normally be. But that was his strategy of approximating. He did the same. So it was very similar. He just used a slightly different notation.